Okay, well, today is Thursday, April 16th. This is actually take 2 of today's lecture. I knew there would come a time when I forgot to press the record button, so that day was today. But I recorded the second half of the lecture, but I just forgot to record the beginning. And so that's why you will have 2 files for today's lecture. Okay, so to begin with, well, what we're going to talk about for today and then for the rest of classes, for the most part, is the topic of non-parametric estimation. And so we're starting with kernel density estimation, and then we'll do regression. And the reason is kind of simple, because the regression estimator actually uses the kernel density estimator, so it's logical to start that way. So this is called like non-parametric density estimation. Okay. And one non-parametric density estimator that you've probably already had some experience using is a histogram. So a histogram estimator, so that's, a histogram. Okay, and so the histogram estimator, this would be the x's. And so you would bin x naught plus h, where h is equal to the bin width. Bin width. And this is sometimes also called a bandwidth. Bandwidth or smoothing parameter. Because actually you can kind of control the smoothness of the histogram by how big the h is. Okay, and so the density times h would be approximately equal to the fraction of the data that lie within the bin. Okay, and so that motivates, so that's like approximately equal. And so we will study this histogram estimator, which is f hat of x naught, which is 1 over nh times this indicator function. Okay, so this is going over all the data. And notice that this method of estimating the density is a local method, because we're going to construct this estimate point by point. Okay, so this is called a pointwise estimator. Okay, and it's also, that's why it's considered a local method. So what things would we like to know about the estimator? I mean, 2 desirable properties. Well, overall you want it to be consistent, okay? Then usually after that you might want it to be, asymptotically normal so that you can do some test statistics. But we're going to concentrate on consistency, just because there's the limit to what we can do in this class. But consistency is already a lot, just showing consistency. We're going to show that it's unbiased. And then we're also, so unbiased asymptotically, it's actually a biased estimator in finite sample, but will derive conditions under which the bias shrinks to 0 as n gets large. And then the other thing, well, that's not enough, just showing it's unbiased. You actually also have to have the variance goes to 0, because remember, you could have an estimator that's unbiased, but there's no sense in which it's getting better. Like we looked at an estimator like that before. So we need the variance to shrink to 0 and the bias to shrink to 0. Okay, so so first things first, let's look at the bias. We started, I think, at the end of last class looking at this. we're going to assume that these are independent too when we do these derivations. So we have n terms here, 1 over n here, so the n is just going to go away. Okay, so this is just writing out the definition of what is the expectation. Now, an integral is just summing things up, you know, and we can see here that this is only 1 if x is in this interval. All right, so we can just write it so that the limits of integration are x naught and x naught plus h here, okay? All right, and at this point, we're trying to estimate f of x naught, even though the x naught may be hard to see with my handwriting, but this is what we're trying to estimate. So, so we're going to Taylor expand f of xi around the point f of x naught. Okay, so let's see where I can put this. I'll put this here, like 1 over h f of x naught, and we're just going to just this time expand it out 1 term, xi minus x naught, f of xi dxi. Okay. Now this Taylor expansion, it might look unfamiliar, but you actually probably did this in your first calculus course because it's called the mean value theorem of calculus, that you can do this sort of expansion. You know, the f, basically we're saying the f of xi is equal to this. Okay, and x bar is in between xi and x naught. You know, so you might have memories of your high school calculus class or your college calculus class whenever you took it coming back to you, because that's called the mean value theorem. Okay, so x bar between xi and x naught. Okay, so so now at this point, oh, actually, you know what? We don't need this f of xi because that's what we were expanding. So sorry, that shouldn't be there. This is just dxi. Okay, so now let's write out what these separate terms are. So we've got 1 or f of x naught over h times this integral dxi, okay? And this integral integrates to h, okay? So these h's are going to cancel. So the leading term is naught, okay? So this integrates to h. Then we've got, for the next term, we have 1 over h times this integral times f prime of x bar, xi minus x bar, dxi, okay? And this is what's called a remainder term. And it depends on x naught, and it also depends on h, because these limits of integration should be x naught and x naught plus h. Okay, that's the remainder term. So to show that this thing is unbiased, we need to show that the remainder term goes to 0. Okay, that's the key. Sorry, I can see the computer puts a little bit of a glare on the board, but it's just highlighting that part. Okay, so our goal is we have to say, under what conditions will this remainder term go to 0? Okay, so let me not erase this step. So let me just write it up here so you can see. So the remainder term we can always write this, well, let me write remainder term, R X naught and H. R X naught and H is less than or equal to, you can always put absolute value signs here, okay? Because we're just summing up things. So if we make them all positive, you know, that could only be bigger if you're summing up. Because if you have plus and minus, you know, those would offset each other. But if we put absolute value, that can only be bigger. So we can say this remainder is bounded by this, okay? We're going to assume that this is less or equal to some constant. So that's saying the first derivative is bounded. And then this here, because xi is only ranging in between x naught and x naught plus h, is less or equal to h, okay? So this h cancels with this h, but we still have another h from the integral, you know, because remember this thing integrates to h because we have dxi out here. So the overall thing is less or equal to c times h squared divided by h, okay? And in the notion, or in the notation that I had last time, we would say this is little op of h, actually. Okay, this goes to 0 as h goes to 0. Okay, so for this estimator to be unbiased, we need, okay, so for bias to shrink to 0, we need the bandwidth or the bin width going to 0. Okay, so that says like for a histogram, as I get more data, I would want to have smaller and smaller bin widths. Okay, so that might seem kind of intuitive, you know, and I think the software, like the art software, does that automatically, that if you have a larger data set, it just automatically makes the histogram like finer, you know? Okay, but this says formally that for that to be a consistent estimator, we need the bandwidth to shrink to 0, and then the remainder term shrinks to 0, okay? In that case, you know, the expectation is just f of x naught. So this is an example of a biased estimator. You know, this is the bias. So for finite samples, so, you know, because empirically when you implement it, you have some h that you chose. Okay, so there's going to be a bias term. But if I choose h in a way that it gets smaller and smaller as my sample size gets large, then asymptotically it's unbiased. Okay. So now the other key thing we have to show is the variance. Because just bias shrinking to 0 is not enough. We also have to have the variance has to go to 0. Okay, luckily the variance is actually not that hard to analyze because we already analyzed the bias. It turns out like a similar expression comes up in the variance, okay? So let's see. Trying to follow similar notation what I have in the notes. So variance of f hat of x naught. Okay, so we're looking for the variance of 1 over nh times the sum times the indicator xi in this bin. Okay. So what we're going to use here is we're going to simplify this sum. So if I take the variance of x, that's equal to e of x squared minus e of x quantity squared, okay? This is positive always because we're taking something and we square it. So this can be less than or equal to e of x squared, right? So we can show that the variance shrinks to 0 if we can show this first term shrinks to 0, because this is going to dominate the variance. So this is actually an application of what's called the dominated convergence theorem. Because the variance has to be positive. Okay, so we're using that dominated convergence theorem. That's what we're applying. So basically we're lazy and we don't want to have to analyze so many terms. So you can think of this as making your life easier. You just say this is dominated by this other function. It's at the bottom is bounded away from 0 because it's a variance. So now we just show this shrinks to 0. Okay, so that's going to be the strategy. So this is going to be, so the expected value of this object squared, okay. Well, maybe I'll just write it right away. So we're assuming that there's no like covariance terms because everything's independent. There is a literature that does non-parametric estimation for dependent data. Okay. Well, this is going to be, this variance is going to be 1 over n squared h squared times the variance of this indicator function. Okay, see this n is going to cancel with one of these n's. So we have 1 over nh squared. I'm using independence because otherwise we'd end up with these covariance terms. I just want to say there is a literature that does non-parametric estimation with dependent data. You know, we offer another course in the ECON department, ECON 221, which deals with time series data. So there are even books, you know, about, you know, density estimation, everything with time series data. It's just, it's a little simpler, you know, since we're doing a micro econometrics, we'll just assume it's IID, then you get, it's simpler to derive the results, okay? And this is going to be less than or equal to, so this is applying this idea here, 1 over nh squared times the expected value of this indicator function squared, okay? And the indicator function squared, 1 squared is always 1, okay? So I don't know if I mentioned, but this indicator function, it takes on the value 1 if xi is in this. When this is true, this is 1, otherwise it's 0. So 1 squared is going to be 1. So you can just take off the squared. Okay, and we already analyzed, so we already showed okay, the term we analyzed before when we looked at the bias, it was actually 1 over h times the expected value of that indicator. Okay, and we showed that that was f of x naught plus a remainder term. Okay, and this remainder term was bounded by h, you know, because the remainder term went to 0 as h went to 0, the bandwidth, okay? But now we have this indicator function here, but without this 1 over h, okay? So this is actually going to be, this by itself would be like h times f of x naught, okay, plus some remainder term, which is bounded by h squared, because we're multiplying everything by h here. Okay. So this part here is bounded by some constant term. So we're assuming that f of x naught is bounded by a constant term divided by, so it's c times h all over nh squared. So this h cancels with one of these h's. So the key result is we require that nh has to go to infinity for the variance to shrink to 0. Okay, So, and that's everything for consistency. So we showed that there are two requirements. Okay, the bias goes to 0 as H goes to 0, and the variance shrinks to 0 as NH goes to infinity. Okay, so altogether, like, what have we assumed in order for this estimator to work? Well, we assumed the first derivative exists because we had f prime. We assumed the first derivative was bounded. You know, we assumed that before when I did the bias. Now we assumed the density itself was bounded. And now we see we have to assume H goes to 0 and NH goes to infinity. Okay, so what does this imply? Well, would H equals 1 over N, would that work? Would that be a possible sequence that I could use if I chose H this way? Okay, well, this would satisfy H going to 0, but it would not satisfy NH going to infinity, right? Because NH going to infinity, see here, N times H would be constant. So that it would be, the bias would shrink to 0, but the variance wouldn't go to 0 if I chose this. But a sequence that would work would be something like H equals 1 over square root of N. That would satisfy H going to 0, and it would also satisfy NH going to infinity. Okay, so there's actually a whole sequence of H's that would work, you know, so it's pretty flexible about how you choose H, but you have to make sure like it satisfies these two conditions. Okay, so I would just suggest, you know, kind of going through the proofs yourself. And I personally find it helpful to write it out on a piece of paper. You know, like, of course you save the trees by, you know, just looking at your computer screen, but I think that it transfers it into your mind a little bit better if you actually write it out. So maybe you can use some scratch paper or something and just kind of go through the steps of the proof, because all of these proofs kind of use similar techniques. But you see, there's a bias variance trade-off, because small h leads to small bias, but small h leads to larger variance. See, because you divide by h. Okay, so with these types of estimators, they're different from parametric estimators, because for the OLS estimator, there's actually no bias, right? It's the best linear unbiased estimator. Here we have a bias, but it goes away asymptotically. But when we choose the H, you have to consider bias versus variance. Okay, that's a trade-off. Okay, and then the other thing I wanted to show you, let's see if I can show you on the, let me try to share the screen, okay? Show you on the R console. Okay, so let's generate some data. So here I generated, well, I did it for two different sample sizes. So let's just do it R norm. Okay, so if you do plot histogram of X. Okay, so I think I have to share a different screen for you to see the plot. Okay, so that's the plot. All right, so that's the histogram estimator. So that's the estimator we've been talking about. Let's now do more data. Zero, one. Okay, and then I'll do plot of the histogram with more data. Okay, so this is now for 1,000 observations. you know, so it chooses a smaller bin width, okay? And then eventually we're going to generalize the histogram estimator. We're going to generalize it to use a general kernel estimator. Let me see if I can share the screen again. Okay, so we have this X data. We can plot the density. So the density command, let's see, let's share the screen so you can see the plot. All right, so you can see here that this is the kernel density estimator. So it's kind of like a histogram, but it's smoothed out more. Okay, and here, so this is what we're going to talk about next. This is a generalization, but the histogram is kind of a simple form of it. I mean, it turns out the histogram is not the best estimator, that you can actually do better in some ways, you know, so that's what we're going to talk about next. All right. Okay, so part 2 of the lecture will be on the separate video, okay, because I had to re-record this because I forgot to press record last time. Okay, so in part 2 of the lecture, we're going to consider how to write down a mean squared error and choose the bandwidth optimally. So we'll be starting part 2.